Well, thank you for watching here. Now what this next 10 minutes should do is help you understand how to draw a force diagram and then how to add those force vectors together. Um, this often becomes the first step in many of the story problems we'll look at. And really a lot of the problems can be broken down to, is this a problem where the forces balance? Is this a problem where the forces add to zero or sum to zero? Or does our resultant force vector or our resultant force not add to zero and end up with the object moving or accelerating in some way? So hopefully you have this worksheet. This is really designed to help you with the lab questions. There will be a quiz where I give you a diagram like this. I will give you the vectors and the angle at which they are applied, and then it is up to you to determine if those forces add to zero or what the resultant force would be. Now really the thing I like about this first activity we did is our drawings, our force diagram drawings right here, really look pretty similar to how this lab was set up, where you were trying to center or balance the weights to get that ring to be centered on the table. A lot of our drawings will look like that as we get more into the chapter. So let's take a look at that worksheet. Hopefully you have that here. But what you want to do is understand that we will draw a 1 Newton vector 10 centimeters. So this first vector that we're given, you can do this in any order. I just kind of chose this one first. This 40 grams, which is 0.4 newtons. We will draw a 4 centimeter line using that scale that you were given. Okay, define your starting point, define your reference point. Please make sure you draw the tip of your vector, the tip of your arrow, because remember we add these vectors tip to tail, tip to tail, tip to tail. So there's my 0.4 Newton vector. Really just draw it anywhere, just make sure you establish your starting position. Now the second vector, that was the first vector. The second vector that I am drawing, it will be, what is that, 12 centimeter line? Because it's going to be 1.2 newtons. But the way to decide how to draw it based on our diagram, I really think of it like you're just taking this force and adding it to the next, so I'm adding it right to the tip of that. The angle that you established on your force table for this one, or for this example, was 125 degrees between those two. Which means when you draw it on paper and using your protractor, I really kind of think of it as the inside angle. So if you looked at how we slid this vector down and added it to the tip there, that angle is 125. That inside angle becomes 55. It's the supplementary angle. A lot of students think of it that way. So you got to line up your crosshairs right on that tip of your vector. You have to establish the direction you're drawing your next vector in. So there's 55 right about there. Now the line I draw will be 12 centimeters. So using the protractor, there's that angle at 55, there's 10, a couple extra centimeters gets me to 12. Once again, please make sure you establish the tip of that vector. That is a 1.2 Newton vector, and that angle was at 55 degrees. Now if we just stopped there, really the whole force table, your whole thing would fall over. All right, your forces aren't balanced. Remember, what we say when things are balanced is that the forces add to zero, or what that means on our adding of force vectors, that means we start and stop in the same position. That's how we establish that they add to zero. So this third vector that we're going to draw, this third vector is going to be 10 centimeters, and the angle, it's not going to be 160. The angle we'll look at on our protractor will be the 20-degree angle. And once again, the way it makes sense in my brain is it's just like you're sliding that rope, sliding that string down. The tension force in that string is added right to the tip. That outside angle stays 160. That inside angle, that supplementary angle, is 20. So that's the angle we want over here, is about 20 degrees. So take your protractor, line up those crosshairs. Make sure you're looking at the right scale. There's my 20 degrees. I just put a little point there. And I make sure right from the tip, I add the next one. Make sure you draw it at the correct angle. So I'm going through my little line. Now this one came out really, really close. If you look at my starting and stopping position, are almost exactly in the same spot. Now these don't make perfect triangles, because once again we are just kind of using lab data. But this start and stop are really close. So do my forces, are my force vectors summing to 0? Well, quite honestly, with the scale we're using, that's about as good as we could get. That ring you just saw, if you looked at the strings, really weren't connected totally. There's that little ring there that could have been off center just barely. But once again, that's really about as close as we could get. Let's try one more example. And this is the kind of thing, once again, you'll be expected to do on the quiz. Given a force diagram, can you determine the sum of those force vectors? So the second one, hopefully you've tried it maybe, but yeah, I'm just going to start with that 0.6 newtons, 6 centimeter line. Doesn't matter where you draw it. Get your tip. Once again, just establish what we did. It was 0.6 newtons. Always make sure you define your reference point, define your starting position. Now, the angle on our paper says 150. But when I draw the second vector, looking at my protractor, I am going to use a 30-degree angle to draw that, to sum these up. Once again, I just think of it like you're sliding that rope down and attaching it right to where the other one was pulling from. So line up your crosshairs. 30 degrees is about there. Put a little dot just so you know which direction to draw your line in. The second force vector I'm drawing, so that's what my two slashes represent. My second force vector coming off at 30 degrees. Yep, established that. Let's draw a 6 centimeter line, 0.6 newtons, 6 centimeter line. Oop, a little off, my protractor scooted. Yeah, so not great, but yes, there's my 6 centimeter line. Remember, that's 60 grams, if you kind of remember the mass that we were hanging over the edge. That was the second vector. And once again, that angle was 30. If we just stop there, that's not balanced. That would fall over, it would tip over, it would start accelerating. But adding this third force to it should get us back to 0, back to our center, back to our starting point. My third vector will be 3 centimeters. And the angle will be 100 degrees. So yeah, just kind of looking at that's going to be close. So get your crosshairs right on the tip. Make sure you're following the right scale. 100 degrees. It's going to be past 90. It's got to be here. Here's my 100 mark. So if you're still having trouble reading those protractors, let me know. But yes, in that direction I draw a 3 centimeter line. Lots of ways to measure that. Just make sure, find your point. There was my little 100-degree mark right there. It's 0.3 newtons, or for this scale it was 3 centimeters. That's not bad. So there's that third vector. It does pull us back to the beginning. This one may have been off center slightly, but things we'll start considering here. There is some friction in those pulleys a little bit, especially as they kind of pull at odd angles on those tables, so that could account for it not balancing totally perfectly in this drawing. But once again, if you remember how we've kind of set up this whole activity, that ring that we were using, if you were within that distance of the ring, that's about as good as we could get. Quite honestly, that's about as balanced or about as close as we could expect those forces to be. So are they add to 0? Well, I would say it's really pretty close. A lot of the story problems we'll start looking at, we will have to draw a force diagram. We will have to add those force vectors together. And a lot of them, we are going to establish that the forces are balanced, or we want the forces to balance, would be quite often what the problem is. So getting used to the notations, getting used to adding vectors tip to tail, being comfortable with how to determine those angles are the skills you really need to move on in this chapter. So once again, I really kind of like this activity because these steps are really the beginning steps for any of our story problems. And once again, just looking at that ring and looking at the tension force in those ropes due to the mass that was hanging, that becomes a good guideline or a good way to establish the problems we'll see in the future. But thanks for your time. I hope this will help you with the quiz.